Glade Company normally produces 8,000 units per month. It's important to note in a special order problem what the company's capacity is. And the capacity for Glade Company is 10,000 units per month. So they've got excess capacity. These are the costs for producing their product that were given to us in the problem. We have fixed selling and admin as well as fixed overhead. So realize that these costs have been unitized at the current production and sales level. The rest of these abbreviations I'm sure you'll recognize from previous problems. So full cost or total cost of producing one unit and selling it is $13.75. Glade Company normally sells their product for $15 a unit. Now in this problem, Glade Company has gotten an order from overseas where somebody wants to buy 2,000 units. It's a big order, 2,000 units, but they're only willing to pay $12 a unit. At first blush, you would say, no way, we'll lose money on that sale. But as usual, before you make that decision, you need to consider the behavior of costs. What you really want to know is how much would it cost you incrementally to build another 2,000 units. Variable costs will increase, but fixed costs generally won't. So, general rules of thumb up here for special order situations. Usually your fixed costs are irrelevant in a special order situation because by their nature, fixed costs are going to be the same whether you continue to produce 8,000 units or whether you produce 10,000 units. So producing another 2,000 units is not going to change your fixed costs. And that's why in a special order situation you need to pay attention to the capacity level. If by producing a special order a company has to put on another shift or rent space somewhere, then obviously some of the fixed costs could become relevant. So let's look at each one of these items and ask ourselves, will this cost increase if we build one more unit? Certainly the cost of direct materials, direct labor, variable overhead, and variable selling and admin costs will increase if the company produces and sells additional units. We know that the variable cost of production will be there. The variable selling and admin costs, well, that's going to depend on the story and the problem. Maybe that's a commission, and so it may be that on this special order you won't have a commission because the customer contacted the company directly. All of that depends on the facts of the problem. But in general, all of your variable costs are going to be relevant. All of your fixed costs are going to be irrelevant. But remember to read the specific situation in the problem. What we've come up with in this problem is a relevant cost of only $7.50. So basically the way it looks is as long as Glade Company can sell the products in a special order situation for more than $7.50, they should say yes, they're going to make a profit. They wouldn't want to drop their selling price to everybody to something less than $13.75 because somewhere along the line they still have to cover their fixed costs. But for a special order, the minimum amount they should accept would be $7.50. Now we have to finish the problem. We still need to determine by how much their monthly profit is going to increase if they sell this extra 2,000 units for $12 each. It's pretty easy. Here's how you do it. The special order selling price is only $12 a unit. It's less than their regular $15 selling price. You compare that to only the relevant cost of producing each incremental unit over their normal production. The increase in net income should be $4.50 times the 2,000 units, or they should see a $9,000 increase in net income, even though they're selling the products for only $12, and at first blush that appears to be less than cost. If they say no to the special order, they've really walked away from $9,000 in net income. Let me show you a longer approach to the problem, which basically will serve as a proof that our answer was correct. This column is without the special order, and slightly to the right here is the column with the special order. So without the special order, their sales will be 120,000. That's 8,000 units times $15 each. Variable costs would be 8,000 units times $7.50 each. The 750 is 250 plus 3 plus 50 plus $1.50. So I've included manufacturing and non-manufacturing costs here. This is all variable costs. Fixed costs are unitized here. So fixed costs would be at 8,000. That's what we unitized them at. Fixed costs would be $2 and $4.25 or $6.25. So ununitizing it puts it back to total fixed costs of $50,000. 120,000 minus our costs is $10,000 profit without the special order. Now, what changes? If we produce 10,000 units, we're going to increase our revenue by 2,000 times $12 each, or $24,000. So this is the revenue just on the special order. Variable costs will go up by $7.50 per unit. So now I've got 750 times 10,000. Fixed costs you have to pay a little bit of attention to. You don't multiply 625 times 10,000 because remember, the 625 was unitized assuming production and sales of 8,000. Fixed costs are fixed. It's going to be 50,000 no matter what. You would have to compute a new per unit cost for 10,000 units if you needed to use that information for some other purpose. So first you really need to go back to thinking about fixed costs non-unitized. They'd stay the same regardless of producing the 2,000 extra units. Net income for 10,000 units, $19,000, and you can see here our $9,000 increase in net income by accepting the special order. Now there's one more part to this question. It says, assume the company has 500 units of the product left over from last year that are inferior to the current model. The units must be sold through regular channels at reduced prices. So you know you've got this old inventory and you've got to get rid of it. And the question is, what's the least that you'd be willing to sell this product for at this point? What unit cost is relevant for establishing a minimum selling price for these units? Well, let's relook at our list of costs in light of this new environment. We know that fixed costs were irrelevant before, so they'd certainly be irrelevant again. But what about the rest of these costs? What's relevant? You've got old inventory sitting on the shelf. Well, what you need to realize is those units have already been built. So the cost of materials, labor, and overhead has already been incurred. Those are all sunk costs. So those are all irrelevant for this particular decision. The only additional cost that's going to be incurred as a result of selling the old inventory is the variable selling and admin cost of $1.50 per unit. So if you have old inventory, the minimum selling price would be the $1.50. As long as you can sell them for more than $1.50, you're better off than if you just left them sitting there on the shelf. So this is an example of when even things like direct materials and direct labor and variable overhead might actually be irrelevant costs. So there's lots of sort of standard setups, hints, and patterns that will help you become efficient at solving these problems, but I think the key is to remember to read the facts of each problem separately and just ask yourself, what will change if I make decision A instead of decision B? And that should guide you through all of these types of problems. Morel Company is trying to decide whether or not they should sell the Marifalon right now in its current state, or whether they should continue processing it into a different product that it can sell for more money. This is a very simple example of a type of problem called sell now or process further. In these types of situations, the joint costs are going to be the irrelevant costs. By joint costs, I mean all of the costs incurred up to the point where you have a decision to make about whether you're going to keep this product in its current state or process it further into something else. Joint costs are all costs up to the decision point, basically, the split-off point. Another way to think about it is it's called a joint cost because these are costs that are costs of the Marifalon or whatever new product you're going to produce if you keep processing the Marifalon further. Joint costs are irrelevant because they're sunk costs. They've already been spent before you reach the point where you're trying to make your decision. So how do we do the problem? Well, let's set up our two alternatives, sell now or process further, and take it from there. This top schedule is the cleanest way to look at the problem. All I've included here are relevant costs and relative revenue items. Here's the two alternatives, sell now or process further. If you sell the Marifalon now, you can sell it for $40,000. To process it further, you'll be able to sell it for $60,000, but it's going to cost you an additional $13,000 to get the Marifalon to the selling point where you can sell it for $60,000. So, sell now, $40,000. Process further, $47,000. In this case, these are income numbers, so our decision is we're better off by $7,000 to go ahead and process the Marifalon further. Now, as you saw in the simple make or buy problem I did as an introduction, it shouldn't change your decision to include irrelevant costs. So here's an example of the same analysis, only I've included irrelevant costs. So the irrelevant costs were the $10,000. That was the 1/3 of the $30,000 processing cost that it cost to take Krypton to the Marifalon stage. So there's $10,000 worth of irrelevant costs, but I've included them in both columns. So the differential answer is the same. You're still better off by $7,000 to process further. And you could also do this on a per unit approach. There's always going to be a multitude of ways in which you can do the problem. I think this top table is the cleanest and the simplest. And we have Shelby Company producing 3 products, X, Y, and Z, and you have information about each one of these products. The bottom line question here is which orders would you advise the company to accept first? Orders for product X, Y, or Z? As a general rule, when there is no limitation, when there's no scarce resource, a company wants to produce and sell the product that has the highest contribution margin per unit because that's going to maximize their profit. So if there's unlimited demand for all of your products, you want to produce and sell the product with the highest contribution margin per unit. Shelby Company faces a slightly different situation. We're going to assume, oversimplify here, that there is unlimited demand for products X, Y, and Z, but here we have a scarce resource. The scarce resource in this problem is raw materials. Scarce resources can be raw materials or they can be labor time. Maybe you need really experienced labor to produce your product. Could be almost anything. Materials and labor would be the two most common. In a scarce resource situation, this is the rule that you want to remember. The rule is produce the product with the highest contribution margin per unit of scarce resource. So it's not the contribution margin per unit, it's the product with the highest contribution margin per pound of raw material or per hour of direct labor, whatever you measure the scarce resource in. So let's illustrate that. Here, raw material is our scarce resource. So what we need to compute for X, Y, and Z is what's the contribution margin per pound of raw material. The problem gives us the contribution margin per unit. We need to figure out how many pounds of raw materials it takes to build one product X or one product Y or one product Z. So down here is information that was given to you in the problem. We know that for product X, they spend $24 on direct materials. That comes from the table in the problem. And down below in the text of the problem, it tells you that the raw materials cost is $3 a pound. So if I take that $24, divide it by 3, that's how I can figure out product A requires 8 pounds of raw materials. Z only requires 3 pounds and Y requires 5 pounds. So with this information and the contribution margin per unit which was given to you, we can complete our schedule. Here are the numbers. I've just filled these in directly from the problem, and you can see that the contribution margin per pound of raw materials is $4 for product X, $2.80 for Y, and $7 for Z. So what this tells us, the answer to the problem is, first the company should fill all orders for product Z. If there's unending demand, it should produce only product Z. But if there is some limitation to demand, it should produce as much Z as it can, and then it would switch to X, and then it would switch to Y. And filling orders in that way will maximize the company's profit. Let's prove that. Here's an additional schedule I built just to prove our work. There's only, in the problem it tells you that the reason this is a scarce resource problem is that there's only 5,000 pounds of the raw materials currently available. So if you take the 5,000 pounds of raw materials and figure out how many units you can produce with 5,000 pounds of raw materials for each product, you get 625 for product X. And that's basically the 5,000 pounds divided by, it takes 8 pounds of raw materials to build 1 unit X. So 5,000 divided by 8 is my 625. So I can build 625 units of product X. I make $32 profit on each of them. Total contribution margin, if all I did was produce product X, would be $20,000. Let's go over and look at Z, since that turned out to be our best product earlier. If you have 5,000 pounds of raw materials, product Z only takes 3 pounds to build 1 finished unit. So you can build 1,667 units of product Z. That's 5,000 divided by 3. 1,667 times the contribution margin per unit gives you the highest contribution margin of our 3 products. So this is just a proof that this is the simple approach, the way to compute which product you ought to be focusing on when there's a scarce resource. We have Dial Company that's producing a small electrical part that it uses in the production of its tractor line. And traditionally, Dial Company has produced this part itself. So here we have a schedule of costs that come directly from the problem. All of these costs are unitized at 60,000 parts per year. So the problem gave to you cost per part for direct materials, direct labor, variable overhead. It gave you cost per part and total cost for direct fixed costs and common fixed costs. The common fixed costs were 135,000. If you divide that by 60,000 parts, that's where this cost per unit comes from. The direct fixed costs in total were 180,000. Again, divide by 60,000. This is your cost per unit. The other information in the problem was that of these direct fixed costs, 1/3 will go away if Dial Company buys the part instead of manufacturing it itself. So $1 will go away. The other $2 of the cost are sunk costs. Or to say it another way, $1 of the $3 is relevant, $2 of the $3 is irrelevant costs. Which other of these costs would be irrelevant? Well, if you stop making the part, the cost of direct materials, direct labor, and variable overhead ought to go away. But the common fixed cost, that's irrelevant as well. Common fixed costs are just allocated fixed costs. They're going to be there whether or not you make or buy this part for your tractors. Let's look at the analysis. The first one I did has our 2 alternatives, make and buy. And in this first attempt, I've included all costs, whether they're relevant or irrelevant. And again, this is a safe approach. This is the easy approach. If nothing else, it very clearly indicates to you what's relevant and what's irrelevant if you first do it this way, side by side. So, cost of purchasing the part, nothing if you make the part yourself, $10 if you buy it. I've added in materials, labor, variable overhead just in the make column. And then for direct fixed costs, notice that if you make the part, your direct fixed cost is $3 per unit. If you buy the part, 1/3 of that will go away. So what you're left with is just the $2 per part cost. Common fixed costs are the same regardless of whether you make or buy. Those costs will still be there. So the difference between the two columns is $1.75. Here we're looking at costs, so a low number is better. We're better off by $1.75 per unit to continue making the part instead of buying it. 1.75 times 60,000 units is the expected difference between the two. So in total, we're better off by 105,000 to make instead of buy this part. Now if I asked, what's the most dial company should be willing to pay for the part? Remember that what you want to include is only the relevant cost of making it. So a better way to approach the problem would be to only include the relevant cost. We know common fixed costs are entirely irrelevant because we have the same number in both columns. $2 of the direct fixed costs are also irrelevant because we have $2 of direct fixed costs in each column. So this makes it clear that I can leave these numbers out of my relevant cost comparison. This schedule is cleaner and it only has the relevant cost information in it. And notice that if I've done everything correctly, I should have the same difference between my two columns. So once again, I say we're better off by $1.75 per part, or $105,000 in total, to continue making the part instead of buying it from someone else. But now I can also say that the most dial company should be willing to pay for a part is $8.25, because that's the amount by which costs will decrease if they buy instead of make.